I would like to thank the organizer to give me a chance to give a report here. My title is on integral differential algebras. This is a joint work with Li Guo and Max and Shanghua doctor. This is my outline. It has two parts. The first part is about the construction of free integral differential algebras. It includes the definition of integral differential algebras and some examples, and also the method of global Kirchhoff basis to construct free integral differential algebras. And the second part is about a topology on integral differential algebra, indeed on commutative integral differential algebra of weight 0. It includes uniformity and its induced topology on integral differential algebra. As applications, we get the divided powers, compositions, exp, and log operations on integral differential algebras. And finally, from the completeness to saturation. This is completeness, you know, is a geometric concept, and the saturation is a purely algebraic concept. Then find the duration of this form. Now the construction of free integral differential algebras. Let us first see the motivation of integral differential algebras. You know, the differential algebra is an algebraic approach to study differential equation per se, but it cannot handle the boundary conditions such as f of 0 is 1. But the boundary conditions such as f of 0 can be handled by differential operator, partial, denoted by partial, and the integral operator, denoted by the integration from 0 to x together. For example, we know the integration from 0 to x of partial f equal to fx minus f0. And so f0 is fx minus the integration from 0 to x of partial f. That is the identity minus the integration compose partial of f. So from here, you know, you can see the boundary condition f of 0 can be expressed by the partial and the integration together. But it cannot express just by the partial. Here, in which we call E denoted by defined by the identity minus the integration compose partial, and called the evaluation. So the integral differential algebra is a simultaneously algebration of both differential and integral operators in analysis, studied at the study of boundary problem. For more details, see the following two papers. The first is written by Marx and Geiger in 1980. I think this is the first paper about the integral differential algebra. The second paper is written by Li Guo, Geiger, and Marx in 1914. In 2014. Sorry, in 2014. Now, the formal definition of integral differential algebras, let K be a commutative unitary ring and the lambda in K be fixed. A commutative integral differential K algebra of weight lambda is a triple R partial pi, where R partial is a differential K algebra of weight lambda. Here we have a weight satisfying the weighted Leibniz rule of this form. In this weighted Leibniz rule, if the weight lambda is 0, it go back to the usual Leibniz rule. And the pi, it is the integration operator. From R to R is a linear operator satisfying the section axiom. That is, the pi, the integration is the right inverse of the derivation. It is the integration is not the left section. Is not the left inverse of the derivation. And satisfying the differential Rothenberg's equation in this form. The differential Rothenberg's equation is a little bit looks strange, but indeed it is very natural from integral by part formula in analysis. This is the integral by part formula in analysis. In this formula, if we let the capital G equal to the integration from little g denoted by pi g. And then the g0, it is the integration from 0 to 0. Of course, it is 0. And the partial of capital G, because of the section axiom, that is the integration is the right inverse of the partial, so it is the little g. So the integral by part formula here becomes, this is the integration from 0 to x denoted by pi, f prime is denoted by partial of f, and the capital G is the pi of little g. And this term becomes fx times gx minus f0 times g0. And the last term is here, the integration is denoted by pi, capital F is capital F. The prime of capital G is little g. But since the g0 is 0, so this term is killed. So these three terms becomes two terms. This is indeed precisely the first three terms of the differential Rothe-Beck's equation. So in conclusion, the differential Rothe-Beck's axiom is abstracted from the integral by part formula in analysis. And as remark, any integral differential algebra R partial pi is indeed a Rothe-Beck's algebra. So what is Rothe-Beck's algebra? A Rothe-Beck's algebra is a pair R pi in which R is a K algebra and the pi from R to R is a linear operator satisfying the Rothe-Beck's equation. This is the Rothe-Beck's equation. In this equation, we don't have a derivation, just have integration pi. Indeed, in the differential Rothe-Beck's equation, here satisfied by an integral differential algebra R partial pi, if we let the u be equal to pi of u bar and then substitute it to the above equation, then here we'll get this equation. Then by the section axiom, the pi is the right inverse of partial. So this is killed and we get this equation. Then we move the last two terms to the left-hand side. That is precisely the Rothe-Beck's equation. So from the differential Rothe-Beck's equation, we can imply the Rothe-Beck's equation. That is, any integral differential algebra is a Rothe-Beck's algebra. Now we will give some examples. The first example is a standard example about the smooth functions. Let R be the R algebra of smooth functions or analytic functions, and the partial be the usual derivation, and the pi be the integration from 0 to x. Then this triple R partial pi is the integral differential algebra of weight 0. The second example is about the Hermite series. So what is the Hermite series? Let K be an arbitrary commutative ring having 0 or positive characteristic. The algebra HK of Hermite series is defined as a K module of infinite K sequence with a multiplication defined in this form. Here, A and Bn is in K, and this is the sequence, K sequence. And then if we introduce the derivation and the integration by the following formula, the partial of this sequence is defined in this form, that is to push left, and the integration is to push right. Then this triple is a HK partial pi is a commutative integral differential algebra. It is also of weight 0. And in the Hermite series, note that as a K module, the algebra of Hermite series is the same as the formal power series Kz. But the multiplicative structure is different, and we have an algebraic isomorphism of this form if and only if the rational numbers is contained in K. The upshot is that one can integrate every element of the Hermite series, whereas the formal power series Z2P minus 1 doesn't have an antiderivative in Kz if K, the base ring, has a characteristic P. So this is why we consider the Hermite series. The first two examples are about the weight of 0. The next example is of arbitrary weight lambda. So let lambda non-equal to 0 be a real number, and R be the R algebra of smooth functions. Consider the usual difference quotient operator partial lambda defined in this form. Here, the partial lambda is the lambda derivation on R. When lambda equal to 0, we obtain the usual difference operator on functions. And further, the usual derivation is partial 0, that is the limit of partial lambda. Now let R be the R subalgebra of the smooth functions that is closed and the operator pi defined in this form. For example, we can take R can be taken to be the R subalgebra generated by E2 minus X in this form. Then the triple R partial lambda pi lambda is the integral differential algebra of arbitrary weight lambda. So that's 3 examples. In the following, we will introduce the global Kirchhoff basis method to construct the free integral differential algebras. The method of global basis or global Kirchhoff basis originated from the work of Berg for commutative polynomial algebras and Kirchhoff for Lie algebras and Harnack for infinite series algebras. But in recent years, the method of global Kirchhoff basis has applied to a larger number of algebraic structures to study problems on normal forms, word problems, rewriting systems, embedding theorems, extensions, growth functions, and Hilbert series. And also, this method, the global Kirchhoff basis method, can also be used to derive free objects in various categories, including the alternative construction of free Rother-Beck algebras and free differential Rother-Beck algebras. This method, the basic idea is to prove a composition diamond lemma, abbreviated CD lemma, that achieves a rewriting procedure to reduce any element to certain standard form. Then the set of elements in standard form the basis of the free object. We will give an example. For example, we establish the composition diamond lemma for the free integral differential algebra. Note that the free integral differential algebra is the free differential Rother-Beck algebra modulo the differential Rother-Beck equation, and the free differential Rother-Beck algebra is constructed by Ligo and Kaya in this paper. So now the problem is that what is the K basis of this quotient? We know free differential Rother-Beck algebra, but now we want to know what is the K basis of this quotient. This is answered by the composition diamond lemma. Now this is the composition diamond lemma for integral differential algebras. Let S be a set of monic differential Rother-Beck polynomials satisfying some conditions. Then the following 3 atoms are equivalent. The first one is S is a global Kirchhoff basis. Here we skip the precise definition of global Kirchhoff basis. And the second term is that for each non-zero element in the differential Rother-Beck idea generated by S, the leading binomial of S is of this form. And the third term is the set RRRS defined in this form. Indeed, that is the set of normal forms is the K basis of this quotient. By explicit computation, for this specific S, that is the set of differential Rother-Beck equations, you can show that it is the global Kirchhoff basis of the differential Rother-Beck ideal generated by S. So, according to the composition diamond lemma, the set RRRS, the set of normal forms, is the K basis of the free integral differential algebra. So, by the method of global Kirchhoff basis, we construct respectively the free commutative and the free non-commutative integral differential algebras on a set in the following 2 papers. Also, the free integral differential algebra on generated by a differential algebra is also constructed directively in the following paper. It is written by Ligo, Gelger, and Marx in this paper. This is generated by differential algebra. Now we come to the second part, topology on integral differential algebras. First of all, we recall some concepts. One is filter, another is uniformity from this Buck's book. A filter on a set is a set f of subsets of x, which has the following properties. The first one is upward closed, that is, every subset of x which contains a set of f belongs to f. The second is downward directed, every finite intersection of sets of f belongs to f. The third one is non-trivial, the empty set is not in f. This is the definition of a field. And the next concept is uniformity. The uniformity is used to introduce the uniformly continuity. So a uniformity on a set X is a filter defined above. On X is a set class X satisfying the following X elements. The first one, every set belonging to U contains the dialog defined here. And if V is in U, then V inverse defined in this form is in U. And the third one, for each V in U, there exists a W in U such that W compose W is contained in V, where W compose W is defined here. And the sets in U are called the integers of the uniformity defined on X by U. Now, two roots to give a topology on a group. In a group, for example, the additive structure in our integral differential algebras, one can introduce a topology and a uniformity via two roots. The first one, root 1, first we give it a topology. For example, you can provide a system of neighborhoods of the neutral element, and these neighborhoods can then be transported to every other group element. Second, after topologizing the group, we can handle it with the right uniformity or the left uniformity or the two-sided uniformity. They all agree for a topology vector space. The topology induced by this uniformity always agrees with the original one. So the root 1 is first give a topology and then give the uniformity. Root 2 is first give a uniformity. For example, induced by the pseudometric by passing to the product space. Second, we get the topology from the uniformity structures, since there is always a canonical topology induced by the integers. Both roots are equivalent in general. Root 1 is more natural, since the topology concept is the more basic concept. But root 2 is after all better, namely more efficient than root 1 in our construction. The reason is as follows. For the root 1 would first prove that the sum and the inverse are continuous. Not that before having a uniform structure, one cannot speak of uniform continuity. Then introduce the integrity, that is the uniformity, and finally prove these and other operations are actually even uniform continuous. But if for root 2, you can skip the first step because uniformly continuous is of course continuous. So we use root 2 in our construction. Now from now on, we assume the integral differential algebras are commutative and of weight 0, but it can be of arbitrary characteristic. And recall in the standard example, the R algebra of smooth function, the usual derivation and the usual integration from 0 to x. You have EF, the evaluation of f, defined by identity minus the integration compose partial of phi. It is equal to f0. Now let R partial pi be an integral differential K algebra and f in R. We define the order of f in this form. Here E is the evaluation. For example, in this standard example, the order of x squared is 2. Here the order of x squared is 2. Now using the order, we can define a function, little d, from integral differential algebra class integral differential algebra to positive real numbers by this form. Then the little d has the following properties. D is indeed a pseudometric on this integral differential algebra. And this pseudometric little d will induce a uniformity on the integral differential algebra via the fundamental system of integers defined in this form. And then the uniformity on R will induce a unique topology on R such that for each f, the nf defined in this form is a neighborhood field of the integral differential algebra of f. So the idea is first that we get a pseudometric, and then using this pseudometric we get a uniformity, and finally we get a topology. Here, little d is just a pseudometric, not a metric. And the topology defined above, we can prove that is compatible with all operations on an integral differential algebra. That is let R partial pi be an integral differential K algebra. Then the addition, multiplication, scalar multiplication, the differential operator, the integral operator, and all operations on R are uniformly continuous. And as applications, using this topology, we can define the divided power on the integral differential algebra. Let R partial pi be an integral differential K algebra and f in R. You can define the nth divided power f to n inductively in this form. The f to 0 is 1, f to n is inductively defined here. Now, this divided power on integral differential algebras has the following properties. This is the same as the usual divided powers. The name of divided powers comes from the fifth term here. This is what called divided power. And using the divided powers, we can define the comparisons in integral differential algebras. So let R partial pi be a complete integral differential K algebra. This complete is with respect to the topology we obtained above. And let F be an element in R and H in the kernel E. E is the evaluation defined in this form. And we define the comparison F compose H in this form. Note that the right-hand side is the infinite sum. But the partial sum sequence, we can prove it is a Cauchy sequence. So we want the integral differential algebra to be complete. Then this infinite sum is well defined. The example. Now we consider the typical example of a complete commutative integral differential algebra. The analytic functions on the real numbers, and let f h be two analytic functions, and with h 0 equal to 0, that is h is in the kernel E is the evaluation. Then f compose h equal to this form. This step is by definition, the definition of the compose, and then equal to this form. This is because of the nth divided power is equal to the h to n over n factorial, and equal to f blue sucker h. This blue sucker is the usual composition in analysis, and this step is indeed the Taylor expressions here. So you conclude that in this example, the comparison defined above is just the usual compositions of functions in analysis. So our comparison is abstracted from comparison of functions in analysis. Now we can also define the exp and log. Let R be a complete integral differential K algebra. We define the mapping exp in this form. Note that this is also an infinite sum, but the partial sum sequence is a Cauchy sequence. So if R is incomplete, this is well defined. And we can define the log mapping in this form, where R star is a group of invertible elements. Then the mappings exp and log are continuous, and the exp satisfying these properties. This is the same as usual exp in analysis, and log satisfying this, the same as the usual log. And the exp and the log are inverse to each other. And using the exp and the log, we can define the exponentiation on integral differential algebras. So let R be a complete integral differential K algebra, and F be invertible G in R. Define the exponentiation F to G in this form. This is exp G log F. Note that here the Fg is just the symbols, and the exponentiations have the following properties. That is almost the same as usual. And finally, we can give an algebraic meaning of completeness, that is saturation. Roughly speaking, integral differential algebra is called saturated if it has enough solutions for all linear differential equations. More precisely, let R partial or R partial pi, R partial be a differential algebra, or R partial pi be an integral differential algebra. A differential subalgebra R0 contained in R is called saturated of R if the dimension of column T is equal to n for each molecule T in this form. This is the maximal dimension of the kernel T. And if all non-zero solutions for U prime equal to UA with A in R0 are invertible in R. And if R0 is R, we simply speak of a saturated integral differential algebra. This is a purely algebraic concept. Now we can prove every complete integral differential K algebra R partial pi is saturated. So this is a geometric concept. This is an algebraic concept. That is, the above theorem can be seen as a propagating a topological rotation of wholeness, that is completeness as a uniform space, to a purely algebraic wholeness concept, that is saturation of the integral differential structure. But the converse of the above theorem is not true. We have a counterexample. The integral differential algebra of smooth functions on the real numbers is not complete, but it is well known that R is saturated. So this is my reference, and thank you.